I have the pleasure to present you the next speaker, which is Professor Petya, who is Professor of Contemporary Bulgarian Contemporary Grammar in the Sofia University. She is also a senior researcher in the Department of Linguistic Modeling and Knowledge Processing in the Institute of Information and Communication Technologies of the Bulgarian Academy of Sciences. And I know Petya from at least 20 years, and we have developed very interesting technologies together. And I think she's one of the best researchers in the field and reference point for syntax and grammar in the Bulgarian language, especially. So, Petya, the floor is yours.
Thank you very much for the presentation. Yeah, I'm very happy that in Bulgaria there is a very, big group of very successful people in this. So modestly, I'm one of them, I hope. So let's start. My idea is as follows. In the first part, I would like to introduce you to the more basic things related to these resources, syntactic resources. Maybe some of you are more acquainted with them, but maybe some of you are not. So I prefer to go with this. And then in the second part, it is something that it is also new for me. I would like to present you some works, how syntax has been incorporated in the big language models, and what the problems are that have been addressed, and so on. And also part of our own work up to now. So yeah, that is my idea. Okay, so as we can see, first I would like to give you some brief intro into the syntactic corpora. What are they? Then very briefly, of course, about the two main approaches that are now available, the constituency-based and the dependency-based. And we'll see that the dependency-based is the one that is prevailing at the moment. But you will also have an invited lecture tomorrow by Joachim Nigel about the dependency, universal dependencies. So my idea is just to briefly go through this, and only if there is time, but probably not, to get into details. Then the types of syntactic corpora, the challenges in converting resources from one of the frameworks to the other, and some conclusions. Okay, so even if we know what a tree bank is, I think it would be useful to see actually what the definition is behind it. So it is a corpus annotated with syntactic annotation. This is the very basic definition, but of course it is more than this. So first, this is the information in the annotation is added or checked by a trained annotator. They started with manual annotation, and what is very specific, the annotation should be complete. Because if you go and see the grammars that you read, for example, for a language, you can see some examples, but usually when there are some marginal ones, they might be not there, right? And you might just say, okay, how I should analyze this one? When you have this resource, you cannot skip anything. You have to have a solution, even not the best, even not the most elegant one, but you should go and do this analysis. So the annotation should be consistent. I mean, if you have one solution for something, you should be consistent with this, even if it's not a good or the best solution. And later on, if you decide to reclassify it, then you can do consistently as well. And okay, the primary format of this annotation is the syntactic tree graph. We will see now what it is. Okay, just example syntactic trees from Wikipedia. It is from Wikipedia because just to illustrate the two main approaches to modeling the syntactic information. On the left, we have the typical constituency one, and on the right, you have the dependency-based one, which is flatter than the one on the left. And of course, there are also other differences, but also similarities. Okay, so what is pro and con concerning constituency and dependency? Again, very briefly, constituency is very easy to read. It corresponds to common grammatical knowledge, the phrases, which is good, but it introduces some arbitrary complexity. The dependency is more flexible. And maybe you know that it is very welcomed for languages that have a free word order. And in that respect, it is flexible and also corresponds to common grammatical knowledge, the grammatical functions. So the focus here is the subject, the complements, the adjuncts, and everything that goes as grammatical role or function. And also, one thing that is not good, it is the problem with headedness. We need some consistent criteria to have a head. And sometimes, and some phenomena are not very okay with being analyzed as headed phrases. But here, always you have to indicate which the head is. So, trees and graphs. A graph is a set of vertices or nodes and edges, and the tree is just sub-graph, so to say, connected graph in which each node, except one, has exactly one parent node. The labels, the nodes and tags can be labeled. Okay, the term tree bank obviously comes from the assumption that this information can be presented as a tree. However, the reality shows that we actually do not present the syntactic knowledge as trees, but as graphs, because it's more complex. And always with the pure syntax, we want to put some more, like it was mentioned in the previous course, like the coreferences or the named entities and the links. If the language is pro-drop, like Bulgarian, for example, and other Slavic languages, we would like to indicate these relations. So yeah, it is more than a tree. And just brief examples with one of the classical tree banks for English, of course, a Wall Street Journal. It is constituent based, and also you can see the bracketing representation. Of course, in order to understand what it is behind, you should also have some knowledge about the annotation scheme, because otherwise you cannot decipher it. Another example is, apart from the bracketing, you can also have this tree representation. And it is interesting because here you can see that I shot an elephant in my pajamas. My pajamas is connected to the verb, but here in the dependency tree, you can see that it is connected to the elephant. And so this is one of the most common ways of presenting the dependencies. So the governing head. So we have an arrow that points to the dependent element. And that's in that way, we can see that shot is the head. And then on the left, you have the subject that depends on it. And on the right, it is the object, which is elephant. And then you can see that in is related or connected to elephant as nominal modifier, but not with the verb. So it's just the other analysis in this representation. And very often it depends on our view on the grammar, because here you see that pajamas is the head, not the determiner, as usual in the theories. And I'll say more about it in a second. Also, just to see other tree banks, how they look like. This is the German tuba desert tree bank. And here, what is the interesting representation, that you have the different way of presenting the syntactic labels, like MP, VP, and also the functional ones, which point the clauses and everything like this. So Germans are very, very unique always, and even in the syntactic theories, they have a special theory with the middle field, forefield, some fields like the initial, in the middle, and the end. And I think it was invented by a person who is even not a doctor, not a PhD. And this theory is very influential, and it covers all their, view on syntax. Okay, another way is the constraint-based grammars that produce also syntactic trees. And here it cannot be seen, but in the next slides you will be able to see. One such theory is LFG, lexical functional grammar, and I like it very much, although I never worked in this framework. But it combines the constituent view and also the functional view, and you can see both, and also the connections, the relations between them. Okay, so here you can see the labels in these two representations. The flatter one, where you can easily read the sentence below, and also the one that in which the words are, floating everywhere. Okay, so if we go further in LFG, as I said, they have the constituency, C structure, and F structure, which is attribute matrix, value matrices. And as you see, they are very complex ones. So usually these formalisms are very, very strong. I mean, they are really the best. However, they are very complex. And in reality, always the people who develop their tree banks in this formalism, they always live with dependencies in the end, because it's really complex representation. Okay, so we now go just for a while on a more abstract level of viewing the things with the tree banks. Let's see how we model the language knowledge. First, language is a natural phenomenon. It is very difficult to formalize. And the good news about it is what? That we have work to do. And we will always have work to do, because we never ever will be able to formalize it completely, right? So then we have the language model. It is a mathematical model, abstraction over the language that already works with mathematical objects, because we cannot see a noun or a verb or a subject and so on. These are constructs. And the relations among them. The linguistic theory is the mechanism that gives us our grammar to the language. Because, there are different linguistic theories, and each linguistic theory tries to prove that it is the best. How? Analyzing, for example, languages in Polynesia or other very rare languages in Peru and so on. But in reality, no linguistic theory is perfect. A tree bank can be defined as a subset of a language model with respect to some unknown linguistic theory. And then when we have a specific linguistic theory, we try to apply it to the language. Okay, so the language model, as we said, is an abstraction over this natural language, and usually it's represented as a set of trees. A sentence representation is a sequence of words associated with a tree, and then a tree bank is rather a set of graphs representing sentences from some natural language. Okay, so about the ideal grammar and the tree bank grammar. Of course, the tree bank grammar aims to become an ideal one, but it can only approximate that. It can never be the ideal one. And here we have some terms like formal grammar is a formal device that for each sentence it predicts whether it's grammatical, belongs to the language or not. And if it belongs, it assigns some structure. An ideal grammar is this grammar that predicts the language with very minimal over and under generation. So not to end with structures that do not belong to the language, but also not to cover only small part of the language. And of course, as I said, we haven't invented the ideal grammar yet. A tree-bank grammar is a form of grammar that generalizes over the sentences in the tree. So it is not the whole natural language, but the data that we have. And if we have to visualize it, we can visualize it like this. You can see the natural language, which is very messy. Then the ideal grammar that tries to cover exactly this messy thing. And then the tree-bank grammar that can solve part of this, but not everything. It covers, it could over-generate a bit or under-generate a bit, but never could be the best. Unless, of course, we work with a controlled language. If we work with a controlled language, we can, of course, model it easily. Okay. So, in order to have a tree bank and to apply some linguistic theory, we should have an annotation schema according to which to annotate it. And this annotation schema is actually the grammar behind this resource. But it could be implemented at least in two ways. One way is to be implemented as a grammar, like, for example, the English resource grammar in the theory of HPHG. There are such grammars also in LFG, or Norgraph for Norwegian, which is LFG based. So these grammars, they usually developed for languages that already have advanced resources for formalizing their language, and then you can produce computational grammar. But, for example, in our case, it was the opposite. First, the annotation schema was developed with the development of the tree bank. And we only could use preprocessing. Christo already said about the preprocessing. If we have the part-of-speech tagger, named entity recognizer, and chunker, the shallow syntax, basically we can have some good initial point to attach the final phrases already into a tree bank. So we could have, in the first case, tree selection when we have a real computational grammar for a language, and in the second case, we have a tree creation. So I had the opportunity to work in both ways. Okay, so the life cycle of a tree bank in general is a design phase, implementation phase, validation, documentation, exploitation, and reclassification, because when you use something, It's always not perfect, of course, and you find new arguments in one or another way, so you can reclassify your resource. And that's why for the, I think for the Dutch tree bank, Calpino, they put on their website who to blame, okay, about the tree bank. Not who to praise, but who to blame about their decisions. Okay, so in the design phase, of course, we can make a tree bank just for the purpose of having a tree bank, but if we want a more focused exploitation phase, then we should know the goal of this tree bank. Then, how deep knowledge would we would like to have into the tree bank, and also the format, because although nowadays it's not a big problem to change the formats into from constituency to dependency or from one dependency format to the other, still you can lose information and also some kind of phenomena. Okay, the result from the design phase is a style book describing the annotation scheme. In case of the tree selection annotation, it describes the discriminators used for the selection of the correct trees. So what happens here? I have a computational grammar, and it parses the sentences, and then all of a sudden you have, let's say, 100 candidates for a sentence. We cannot imagine even how many ambiguities are produced by this for any language. And then if we have this mechanism, then we should have good way of discriminating to say, okay, if I have masculine and feminine in the adjective and noun, then I cannot have a phrase. It should be discriminated in some way. And this is true, as I said, for the computational grammars. Then, in the case of tree creation annotation, then we should look for another way of validating. In our case, it was a DTD in XML, and what is in red, then it's maybe not okay as an analysis. But of course, it is not enough. Okay, implementation phase. We should identify the sources of information which support the annotation process, whether it's a grammar implementation or just pre-processing plus full syntax that we want to annotate, the architecture, the software, the organization of this annotation. And here we could have the text corpora, partial grammars, the chunkers that are very important, general linguistic analysis, grammar books. It is very important. In our case, we consulted all the books that were available at the time. Validation phase, it requires consistency checks over the whole tree bank. These checks determine the conformance with the principles of the style book that are followed and the agreement among annotators. And of course, here we could have two problems. The style book is not good enough, and then the people cannot annotate well because it's not clear what to do. Or the phenomenon is very complex, and then the annotators could have different opinions, but they are correct. And then in our case, we had some preference rules. We could say, okay, both are correct, but please prefer this, but the other is not wrong. The implementation phase, always important, not only for tree banking, but in any application. It should register the current state of the tree bank, and of course, then the people would know what the development is based further and how it might be used. It is again the style book, the analyzed phenomena, the description of the annotation, and so on. And exploitation phase includes the actual usages. Of course, as we already heard, it's not only the linguistic research. When we started, we thought, okay, we will just do it for linguistic research. Tree banks are far more useful for many other applications than just linguistic research. In digital humanities, we saw that in event extraction also and other very useful applications. Okay, for creating other useful language resources and so on. This phase reclassification is very important because, as I said, you can never have a static resource. I mean, you could have it, but it's not good because you add more sentences in the case of tree banks, or you find out that there is a better analysis for some phenomena and you'd like to change it. So it is a dynamic one in this sense. So you could have a creation of a new annotation schema, new data, adaptation to the represented linguistic knowledge. Because when we had to transfer our tree bank that was constituency based to dependency based one, then all of a sudden, because it's a multilingual context, we had um, to conform to decisions that we don't like for Bulgarian, right? But it is always kind of a compromise whether you'd like to be comparable or you'd like to be more faithful to the traditions and the ways you believe your data should be analyzed. So it's a big problem for the people who have to do it. Okay, so the encoded linguistic knowledge, it is not, you say, okay, it's just syntax, but until we just go to the syntax, we have many other things to do before that. It is morphosyntactic information, especially for the rich languages like Bulgarian and other rich languages. The named entities, many tree banks now have also the co-referential chains within and across borders of the sentence, semantic rows and senses. I mean, the richer the tree bank, now the better. So the prerequisites are related to what I said. It would be nice to have these modules already available for a language. Of course, nowadays with the big, large, huge language models and techniques like zero shot and few shot and much work done within the similar languages, maybe it's not that crucial, right? Initially. But at some point, if you don't have the good resources for your language, it becomes crucial. I mean, you can have something initial, but you cannot have really good model without resources for your language. Okay, and here just briefly, I'm just mentioning, but I'm not going into that, about these problems that go before the sentence boundary detection, which is not trivial, of course, especially in dialogues, in direct speech, and so on. Yeah, then to decide what should include the syntax that you analyze with. This is, of course, the syntactic domains and PVPPP, but also maybe functional labels like the clauses, domain clause, the embedded ones, and also the pragmatic elements, discontinuity, and other phenomena. And also semantic rows, discourse information, temporal information that is included here, and so on. Yeah. So here another thing is very important, the full syntactic analysis versus chunking. Chunking is the shallow grammar. Here it is embedded by Avni. And I like this term, islands of certainty, because you get just smaller phrases, but they are sure phrases. And why it is very important? Because, for example, grammars that use HPSG and LFG, they are lexicon based, they are lexicalist theories. If the word is not in the in the lexicon, then all the parse fails. And you would like to have some phrases from this sentence, even not all of it, and not just to have, okay, this sentence is not parsed, it's failed, and so on. So that's why it's good to have these chunking non-recursive structures. And the precision is favored to coverage, of course. And just to mention that now, although the tree banks, and we believe in that at the best, that are manually constructed and analyzed, we also have these parse banks, automatically parse text when we already have parsers, and we have some syntactic structures. At the time, the metaphors were garden, so the manual tree bank is a garden. Then we have a forest, if we have automatic parsing, but then some checkings over the resource, and jungle, if you just parse and not look into that. It was very nice metaphor. And apart from parse bank, we also have another term, cache bank. Yeah, it's really, really automatic and nothing is checked there. Dynamic bank is the best one, I think, but it is related to the computational grammars because you can just construct your grammar and check immediately how it parses and just to correct if there are any errors. I did that for Bulgarian, but my grammar at the moment parses 200 sentences reflecting different phenomena. And usually it happens, you repair one thing and then you get another problem and again and again and again. And so I have this experience, I'm lucky. Okay, challenges. Syntactic domains and ambiguity. Of course, if we want to compare with other languages, this is a problem. A linguistic phenomena, whether we assume that this one is the same phenomena in the languages or different. The clitics, are we the same with the Romance languages or not? And things like this. And relation to other linguistic levels, whether we have monostratal or multistratal approach. Monostratal is you have everything at the same time, which is HPSG and LFG. Just it's very as I said, strong, but it's very complex. Or you have different levels and you have mechanisms to relate them. I tend to, I don't know, I worked in the first one, but I tend to like the second one. I just some example with ambiguity, but we already had this. And of course, this structural ambiguity cannot be resolved on the syntactic level. You need ground knowledge, you need knowledge about the context, the discourse, knowledge about the world, to know, maybe statistically it can be selected, to know that is more often you buy cars with some money, but you don't buy cars that have money in them, right? Although it would be really nice, but not typical, not probable. Yeah, and I already said some words about precise grammar, this computational grammar. It is really so precise that if, as I said, the lexicon doesn't have this word or your rules do not have this rule, then the sentence cannot be parsed. But they are very powerful. So such a grammar, I know that it was developed for English, but it took, can you guess how many years for a precise grammar of English? English, not a morphologically rich language. 30, more than 30. So there are good grammars for Japanese, for Norwegian, and I told you how many sentences my grammar can parse. Okay, so again, about constituency and dependency, phrase-based, word-based, both have problems, common problems, and also both are connected. Because from words you can make phrases, and phrases very often have head words. Okay, so the constituency we have the pantry bank, as I said, and I also mentioned the lexicalized grammars as constraint-based, but also the categorical grammar. They're also, I'm not so familiar with this framework, but also a lot of work is ongoing there. Okay. I think I already showed this. The thing about LFG and HPSG that they have this, especially LFG, this connection with the functions and the constituency tree. And HPSG, you can see what a matrix is just for kin walks. You can imagine if it's from media, some sentence, you can, you know, 3 or 4 levels or lines, it will be look like. And that's why the people who used it, again, I think the Dutch, they just ended up with dependencies. Okay, so yeah, in the dependency-based tree banks, it is important you to know more about the universal dependencies because it is now the state of the art. But I always want to mention the PRAC group because they were the first to inspire into dependency parsing and rebanking. Just to see how their tree looks like. It is multi-stratal because you have all the levels from the words to the top of the tree, dependency tree. Universal dependency, you have more possibilities to see what it is. Yeah, and maybe just 1 minute to go very quickly through the myths and the reality, and then we finish with this part. Myth, tree bank can be theory neutral. No tree bank can be theory neutral. It is always theory dependent, but it could be more light or more depending on the theory, right? Then we can always convert safely the resource from one theory to another. No, you can lose, as I said, information or ways. There are not good ways to tackle the problematic phenomena like coordination, for example, relative causes and so on. We do, no, theory complexity doesn't influence the tree bank presentation. It does. I mean, if it's complex, it's complex. So HPSG and LFG, they are very good for the machines, but not for people. And the other way around. Okay, so the term theory neutral doesn't mean without any theory. It means that another length level of annotation is developed that is applicable to any language. So it is really a light version of syntax, but not just neutral. And yeah, here you have the universal dependencies with the theory. And I can tell you that one of the most difficult queries is the syntactic based query. Because it's powerful, but it is difficult to model this query in some language. And for that reason, for example, I like the best this GRUMACH, let's say, mechanism or system, because they give you by example. You can just choose what you want and get the subject or subject and object or something like this. They have a matrix and you can just choose what you are interested in. Otherwise, you have to really invest your time to know how to do this query to get some syntactic structures. And this is just the current situation with universal dependencies. Just, yeah. And in conclusion, we see that at the moment the dependency tree banks are dominant and the parsing dependency is dominant. So it's good that tomorrow you will listen more about it. And Also, there will be in the afternoon, I would like to say about the afternoon course by Virginica and Evelina. There is current cost action unitype that combines universal dependencies with parsing of multi-word expressions. So they will present to you the really latest achievements on that, which is very nice because everything is related to each other. Okay, I stop here. Okay, so basically I'm doing some overview of papers that I found when they try to incorporate syntactic knowledge into large language models, but in different way. Okay, and then if we have some time, I'd like to present some work of ours, but it is under review, so yeah, just of course any feedback is welcome on that. Okay, so large language models and syntax, ways of incorporating syntax in these models, parsers versus large language models, some in-house experiments and conclusions. So most of these papers actually are in archive. So you know that nowadays they just hurry to put them there just to have their ideas reserved. And some, of course, are published. But the first one is how well do large language models understand syntax? It is over-generated meaning of understand, but anyway, an evaluation by asking natural language questions. Okay, let's see, I always give the authors and the link. But when you get the slides, you can just follow and read more. And don't be surprised, most authors are Chinese. Okay, so what happens? As per boxes, they are research questions. Do these models truly comprehend human language, or do they complete tasks by memorizing surface-level lexical patterns? Do these models understand sentences based on syntactic rules, or do they treat language as merely a bag of words? Whatever I can catch, and that's it. So their approach is question answering templates that they use to understand. So they target 9 syntactic knowledge points, we will see that. And they believe that they are more closely related to sentence comprehension. Experiments conducted on, you see, 24 large language models. They suggest that most have a limited grasp of syntactic knowledge, what we already supposed, exhibiting notable discrepancies across different syntactic knowledge points. So it's not easy for them to understand syntax. In particular, questions involving prepositional phrase attachment, they pose the greatest challenge. Not surprising as well, because sometimes for humans it's difficult. Whereas the adjectival modifiers in direct objects are relatively easier for these models. Okay, again, their findings and methods. They did a case study on the training dynamics of these models, and it reveals that majority of syntactic knowledge is learned during the initial stages of training. Why this is important? Because nowadays we believe that the more data, the better. However, the authors say maybe it's not the silver bullet, maybe it's not the best thing to do. Maybe we need more non-homogeneous data, but not more data always. It's interesting, actually. Two main approaches, probing and prompting. Probing requires access to hidden states of the algorithm of the model, which are not available for these API models like GPT series. Prompting requires designing of complex prompts, we already know that, and sophisticating decoding methods. And also there are literature on that. Okay, so as I said, authors use a question answering approach. And they said, okay, we have three types of questions and templates, true, false, multiple choice, and fill in the blank. Like we test some human. Findings indicate that while most language models have a partial knowledge of syntax, GPT-4 demonstrates exceptional superiority. So this is the winner, according to them. For as data, the constituency trees from the pantry bank were used. So mostly, of course, here the work I present as an overview is on English. I found one paper also on Chinese, but I didn't have the time to go through this very well. But they also investigated different phenomena, how they are grasped by the language models. But since I don't speak Chinese, I decided not to. Okay. So, here you can see what they use actually. From the syntactic point of view, grammatical subject, subject complement, direct, indirect object, main verb phrase, adjectival modifier, adverbial, and it is interesting also to address coordination and prepositional phrase attachment because they are really very tough for any theory. And you have the numbers and also some examples of this. Okay, so the experiments, as we said, were conducted on 24, I mean, many experiments, many models, but these models were from 6 families. And here we can see Mistral, Batch 1, 2, Falcon, Llama and Llama 2, and ChatGPT, which is good because we can see how they behave. So, as we said before, the winner is ChatGPT. And if we go per type, true or false, and multiple choice, and fill the gap, what we can see, except the fact that it is the best, and the second best is GPT 3.5. I think that the best type was multiple choice, if I remember correctly. And the other are not so well. And the worst, of course, is fill the gap. Okay. If we go through syntactic phenomenon, per syntactic phenomenon, which was grammatical subject, direct object, before that it was subject, object, and indirect object, and so on. Again, we can see that the numbers for GPT-4. You can also see the averaged numbers, which is also good indication of what is difficult and what is not. So for this GPT, which is the best, from what I see, it's indirect object, it seems, which is interesting. And the one that is worst is the adverb, which is very interesting. Of course, it's related to prepositional phrases, but it is interesting in our data, in our experiments. Again, one of the problems were adverbials, which I didn't expect, but obviously there is some tendency on this. Okay, so this was very brief indication on this paper. And now we go to another problem, explicitly modeling syntax in language models with incremental parsing and a dynamic oracle. Okay, let's see what these people do. They propose a language model already. They don't test it, but they just propose a new syntax-aware language model, which is called syntactic ordered memory. From what I understood, this ordered memory already existed, and they just built on this. Okay, it explicitly models the structure with an incremental parser. So we need a parser as well, not only model, and maintains some conditional probability from left to right. So it ensures that we go more or less with the standard parsers that we have for a language. Okay, so they train an incremental parser and thus they avoid bias. But on top of that, they also use dynamic oracle to predict the next token, what comes next, and to prevent more or less the model from wrong decisions. And what is the moral here? Experiments show that this syntactic model, ordered model, can achieve strong results in language modeling, incremental parsing, and syntactic generalization tests. And at the same time, it uses fewer parameters. And we will see that it is best on the not on the common phenomena, but the more rare phenomena, which is also interesting. It's good on the more difficult ones. Well, this is something that we already know. So I'm just marking it here that most language models are good at capturing frequent syntactic structures. It's not a problem, but they do not generalize, for example, with long distance phenomena and things like this. So these people want to address this issue. Okay, the proposed model acts, as I said, as a language model, but also as an incremental parser. It inherits the syntactic representation, which is used in ordered memory. And here there is another line of literature that is there, in which syntax trees are embedded in some memory representation. So they embed this knowledge. And if the ordered memory itself is unsupervised, so no data was used to train a parser or a model, this syntactic ordered memory is explicitly trained to predict the syntax trees incrementally, and also they use partial syntactic structures. That's why I said that maybe with these large language models, we slowly go back to shallow syntax before we go to the full syntax again from the 80s last century. Okay, so what does it do next? It factorizes the next token prediction into two steps. How it predicts the next token. First, the attachment position is predicted for the next token with some zero-step look-ahead parser. I'm not specialist in parsers, but obviously we should have one in order to apply this technique, trained on a data supervised fashion, and then the next token distribution is predicted, partially predicted structure. Okay, so from the partial knowledge, we want to get the full tree. Again, data is from Pantry Bank, and there is another corpus that is based on Pantry Bank, this BullDeep, which is a large Pantry Bank style parsed corpus of, you see, 24 million sentences. Maybe that's a jungle, maybe that's this parse bank, cache bank. But they use it very often, I saw through the papers. Okay, it's not well visible, but here it shows that on various phenomena like long distance embedding, center embedding, which was the main sentence and the clauses to detect with subordinators, complementizers, and I cannot see the other things, but there are also such phenomena that are licensing and yeah, this kind of phenomena, they are very well captured by the model. On the contrary, the adjectives, for example, which was the first one, the agreement, is not captured well. I mean, it's good that the model can do well with rare or difficult phenomena, but maybe it's not good that it cannot handle at the same time the more typical structures. Okay, another one. Tree-planted transformers, I think, yeah. Tree-planted transformers, large language models with implicit syntactic supervision. So there is another way. Yeah, the first paper was basically to test how the models understand syntax, and these ones are basically how we could implant somehow syntax into that to become better. Okay, so they say the following. Syntactic language models can be trained efficiently to reach relatively high performance thanks to syntactic supervision. So here we always have data, I mean tree banks that we should train this model on. But they have trouble with scalability. So it is necessary to develop an architecture that can combine the scalability of large language models with the efficiency of the syntactic language models. So to take the good features from both. And that's why they call it syntactic large language models. Okay, so their method is called tree planting. And they say we implicitly plant trees into attention weights of transformer. So this is within the model to reflect the syntactic structures of natural language. Transformer is trained with tree planting, and it is called tree planted transformers. So already they know something about syntax. And the good thing is that this model can learn from small tree banks. For example, our tree bank is small, like 200,000 trees. Sorry, it's tokens and 15,000 trees. But nowadays, you should have like minimum million trees to work with. But it's good that you can learn on small tree banks through this tree planting method and then to apply it on a corpus and to scale it up. Okay. So this model, transformer with syntax, despite the lack of explicit syntactic supervision, they say outperforms various other models with explicit syntactic supervision. So I understand that if you implant this knowledge into the model, it is better than if you train it on the data and just use it. Okay, and I think that this tree planting method is promising one. Okay, the data is some data set that can be found there. And you can see again this big corpus on tree bank, this big one. It's very simplified way what they do, but the details are in the paper itself. So you have a small tree bank with some analysis, and then, of course, you can say, okay, sync is the root, and every other word depends on it. Of course, it is very simplistic way, but when you learned in this way from the tree bank, then you can go to a corpus without structures, for example, dogs in a yard play, and then the model can say, here, play is the root, and all the other words depend on it. They estimate also the relations between the words themselves, but it is in the paper, just for you to know. It is the simplistic view. Okay, so nowadays it's always good when we do something to say explicitly our limitations. And in the big conference in computational linguistics, they always do that because, of course, we never can be the perfect ones. And they say the following: what the limitations are. Um, these big models are trained at the document level. I mean, usually the large models are trained at the document level, but the syntactic language models are trained on the sentence level. So there is some discrepancy on that. And the annotations in tree-banks are really sentence dependent. So there should be some way to make them work together. Also, the evaluation was also limited on the syntactic knowledge benchmark and perplexity, but there are many other ways of evaluating whether this model works well or not. And they think that the development of a novel continual learning method would be necessary also for scaling this model. So it's not only data, we need also algorithms, we need also methods. I mean, not easy, obviously. Okay, the other one is incorporating syntax in pre-trained language model using some optimization. And the idea is just to prevent the model to forget too quick, maybe. And let's see what they do. Okay, here the authors explore additional training to incorporate syntactic knowledge to a language model, and here they use BERT. They designed 4 pre-training tasks that learn different syntactic perspectives. For example, to predict the dependency relation, phrase detection, also main subordinate classification and coordination. Again, it's interesting because coordination is not easy to model. The data here already is from the Universal Dependencies tree banks. We also use this one for English because it was comparable to our tree bank. The following types of sentences were removed as noise. Sentences when they are less than 5 tokens, sentences containing foreign languages tagged as X, sentences containing undefined dependency relations, like a very general one, dependency. So very often you have to clean the data. And here, just to see what happens about all these relations, they just apply different optimizations functions and Adam something is the best one. Optimizing, yeah. But as a whole, I think even if we look at the other ones, they are all good, more or less. Even for coordination, which expectedly is the worst one, it's good. I mean, these numbers seem good to me. Okay, so this was really a very short overview of the papers I found related to how syntax is incorporated or tested in relation to large language models. And of course, I wanted to prove that this knowledge is essential and tree banks are important. And yeah, that's why I just made this overview. Okay, in our case, what we try to do is to introduce shallow syntactic information within graph-based dependency parsing. And there are some experiments that we have done. Of course, there is more to do, but I decided that it's good to share with you the recent things that we are doing. And of course, as I said, any feedback is welcome. Okay, so Here, a new BERT model fine-tuned for parsing Bulgarian text is introduced. This model is extended with a new neural network layer. So this is basically manipulation of the model itself. And the idea is that we want to incorporate some shallow syntactic information during the training phase. And the results up to now show statistically significant improvement over the baseline. Not too much, but statistically significant. The architecture has been designed and tested for Bulgarian, but also for English, because we wanted to show that this method works also for another language. But as I said, there is more to do. Okay, so dependency parsing has been extended to accommodate some predefined shallow dependency information. That is the new part that we import into the model. The predefined information came from two sources, lexicons, valencies and multi-word expressions, but this is really very modest one because we concentrated on the fixed multi-word expressions, not on the really heavy ones. So it is just initial work. And shallow grammars, chunkers, where we have developed at the time our own chunkers, some NPs, BPs, and so on, and we could use them now. So we have some partial dependency trees, and for example, in the partial grammars, for the critics with the verbs and noun phrases that are sure, and so on. Okay, implementation. The dependency parsing that we use is based on large language models. We follow the approach of McDonald, which is from 2006, about the graph-based dependency parsing. And what does it mean? Determination of dependency arcs in the syntactic tree, the immediate domination relation over the tokens. So for each token, we want to see what the parent is, what it depends on. Okay, and then when we do that, to label the selected arcs with the appropriate dependency relations. So this is not a novel approach, this is very popular approach. So we use this. In our implementation, both the transformer model and the head selection model are directly connected. The head selection model is integrated as an additional layer over the last layer of the transformer model because we believe that it should collect as much information as possible through the way and then to take this decision about the heads. The head selection model is similar to any other token classification model, except that the number of classes is dynamic. So it varies depending on information from the data. Maybe it's not very well visible, but it shows the typical architecture. And in the middle, actually, we manipulate this. We put this shell information before we go up and take this decision of head selection. That is basically this picture. Okay. So we worked with two universal dependency tree banks. The one is ours, BTP Bulgarian tree bank, and also the GUM English tree bank. There are several English tree banks, but as I said, we use the one that is comparable as size to ours. Okay, so we selected our tree bank because we wanted to do some experiments on Bulgarian, of course. And we could use our chunk grammars and also some preliminary multi-word expression information. And as I said, it is basically the information that we have in the tree bank, and it is basically fixed multi-word expressions. Okay. For English, we just wanted to show that this algorithm also, this model also works for another language. And in cases, in Bulgarian and English, we show that even when we select arbitrary sure arcs, not specifically defined, even then the results are better. I mean, they improve. And we can imagine if we just have really a lot of sure links beforehand, how it would go. For Bulgarian, we show that it works. For English, we just show by the arbitrary generated arcs that it really improves the results. Okay, so here you can see the experimental settings, pre-trained model with what parameters and encoders and so on. How much the Bulgarian tokens are. So the pre-training dataset consists of mainly web data, literature, administrative and scientific documents, and also Wikipedia articles. And you can see how many epochs and so on. Yeah, I will not read them, but they are there. Okay, for results on Bulgaria data. So in italic, we can see the baseline, which is the best model for a baseline, and then the best model is prompted with 40 links, sure links from shallow syntax. And here we have two numbers. On the left in bold, we have this model with the predefined arcs from our chain grammars and also from multi-word expressions, because we have them for Bulgarian from the tree bank. It really improves the result, not as much as on the right, the underlined numbers. This scenario on the right is not very realistic. It is very nice as a result, but it's not realistic because it is the arbitrary, using the arbitrary links from the tree bank. And the problem here is that we don't control them and we don't know what can happen and how it goes and so on. So it's really just to show that even with arbitrary knowledge inserted into the model, it becomes better. But we aim at improving the one with controlled links from the lexicons and from the tree bank, that we really know what the knowledge, the linguistic knowledge is. Okay, so our intuition is that this reasoning happens in the last layers of the encoder. I already mentioned that, just before the head selection layer. Since the head selection layer predicts the head of each word independently. Thus, no information sharing can happen there. So that's why we get this information from outside sources in the middle layer before we go to the head selection layer. That is the idea. But of course, it's just an intuition, right? So it could get other results from other languages and experiments. Okay, so from our point of view, from these experiments, the lessons are this. Using an arbitrary predefined subset arcs as prompts is sufficient to train the model to recognize the prompts and produce good results. This one is just not there. Anyway, the ability to train with an arbitrary subset of prompts is important, especially when for a language we don't have resources. The fine-tuning training is done for these 10 epochs with a learning rate, with linear decay, and so on and so on. So there could be also other settings. But we think that it is promising direction to go and to see what happens next, maybe to have also experiments with more languages. And just to show the results for English, as I said, here we don't use predefined shallow arcs, but arbitrary arcs from the tree band. And even with 20 such predefined arbitrary arcs, the results are much better than the baseline. Just we show this. And of course, we measure the unlabeled and also labeled ones. Okay. But of course, we did also, I'm very big fan of manual evaluation, very big fan. So nothing goes ahead without this. We have performed some on the baseline model and the best model prompted 40 for Bulgarian. And of course, we try to see the baseline, the errors in the baseline, and the errors in the best model. Okay, the baseline makes errors in, for example, wrong head direction. It should be in one way of direction, but it did it in the other way. I will not go into details because it's very specific to universal dependencies, but it's there. Wrong head selection, we would expect some to be the head because it should learn it, but then it selects the other one. And especially in such constructions like in Bulgarian, like glass of water, Chasha Buddha, of course, both of them are can be licensed as heads. But in our model, the first one should be the head, and the model selected the second one. I mean, otherwise both could be a good solution. Wrong head assignment. Yeah, then wrong root assignment, and of course, wrong PP attachment. So the usual things that would make problem also for a parser. What we see here, where the best model makes errors, very often the types of errors are the same, of course. Wrong head direction is the same, wrong head assignment is the same. But here we also have this wrong non-PP attachment very often, which is interesting for the best model to do that. The adverbials, the problem with adverbials. Just to summarize, as it can be seen from the observations above, both models generally make identical types of errors. At the same time, it seems that the best one has more attachment-related issues, while the baseline more head-related issues. Of course, they can cross, but this is just what we have from the data up to now. Okay, so our idea was to show that the extension of the transformer architecture with some knowledge, even shallow syntactic knowledge, already improves the model. And it is due to the fact that the head selection model is improved. But it is also shows, this is the downside here that we should work on, it is not an extension of the baseline model, the new one. It's not just an extension, but it seems that they cover different search spaces. So at some point, we would like to have a model that extends over the previous one, but not just to have these discrepancies. Okay, and I'm just summing up. Envisage improvement, but not only this. Through the improvement of the prompt attention layer by including more linguistic information and see, of course, at which point it helps and at which point maybe it will decrease, and I don't know. It could be a grammatical feature, shallow semantic information, some ontological information maybe for named entities, and so on. But the important thing here is that it should be reliable. I mean, just to put knowledge that we know it's reliable. Through the extension of the tree bank with new sentences, selected with the help of some active learning procedure, because of course the coverage of some phenomena might not be enough. Through the improvement of the shallow grammar and the coverage of multi-word expressions, lexicon, but really the lexicon with idiomatic expressions and all these problems with the word order and everything that might cause problems as well. And of course, the related algorithms for better prediction and consequent recognition in text. So, really, last of the last, we extended the standard transformer block architecture with a new prompt attention layer, which incorporates some knowledge. As I said, it's modest, not very full-fledged, but still, from external knowledge sources. In this way, it is internally modified to produce a better dependency passing model. And we would like to use deeper syntactic knowledge, improved shallow syntactic knowledge, and also semantic one. And also not only during the fine-tuning stage, but the pre-training stage. Okay, so I think I managed to share with you what I had in mind with this. Thank you very much for your attention.